everyone, we are from Group 4 and would like to present a project on audio noise filtering using digital filters in MATLAB. The objective of this assignment is to design a filter to remove unwanted noise from an ECG signal. To filter the audio, we use IIR Butterworth filters because of their smooth and stable frequency response. In this presentation, we will discuss MATLAB input signal, filter design, Pro 0 Pro, and output signal. This is the given audio signal with noise.
0125.
This is the code for audio noise filtering. In this project, we start by importing and listening to the noisy audio signal to understand the noise problem. We then use FFT to analyze the signal in the frequency domain and identify the unwanted components. To create the audio, we apply a second-order Butterworth bandstop filter to remove a narrow noise band, followed by a third-order Butterworth low-pass filter to eliminate high-frequency clicking noise. After filtering, we combine both filters to analyze their overload effect. Finally, we compute the FFT to observe improvements in the frequency spectrum, save the filter audio, and generate the frequency response and Pro 0 Pros for analysis.
My name is Suggestion. This slide presents the input audio signal in the time domain. The left plot shows the large amplitude fluctuations caused by both the voice signal and noise, and the right plot displays the filter version, which appears smoothed, indicating the successful noise reduction. In the frequency domain, the top plot shows the magnitude spectrum with strong peaks that represent the dominant frequency. The lower plot displays the phase shape of each component, providing insight into the signal structure. This is the code where the signal was loaded using the audio read function and played using the sound function to hear the noise. And the time vector was generated from the sampling rate for accurate time scaling. The signal was transformed using the FFT functions to obtain the frequency and components. The magnitude and phase was extracted using the ABS function and also the angle function and plotted using the plot and subplot functions. This graph helps identify the noise characteristic for the filtering stage.
Since there are two different types of unwanted sound in the audio, we use two different types of infinite impulse response IIR Butterworth filters. To remove the long beep noise, we apply a bandstop filter, so we first set the order to 2 because it's more simple and stable to avoid distortion or delay. From the frequency domain magnitude plot, we observe that the noise appears at 800 Hz. So we select the cutoff frequencies at 780 Hz and 820 Hz. We convert this lower and upper cutoff frequency in Hz to radian using the formula omega c equals to 2 pi times cutoff frequency divided by sampling frequency, which is 8000 Hz. Then the normalized cutoff frequency Wn for the MATLAB code will be 0.195 and 0.205. The bandwidth is 0.01 pi radian. Here, BBS represents the numerator coefficients B, while ABBS represents the denominator coefficients A of the filter's transfer function. Butter function designs the filter, and the filter function applies the filter to the audio signal. Next, we apply Butterworth low-pass filter. Third order is chosen to remove the clicking sound at around 2400 Hz without overfiltering the audio. Cutoff frequency and bandwidth were set to 0.35 pi radian, as this ensures that most of the signal passes through, while higher frequency click sound is attenuated. Then, normalized cutoff frequency Wn for MATLAB code will be 0.35 for this low-pass filter. After that, we combine these two IIR filters. Numerators BLB and BBS from each filter are combined. Denominator ALB and ABBS are combined as well, both using convolution. B and A are the new coefficients of the combined filter.
In this assignment, we have experimented different type of filter, like FIR with 500 orders, but it has the higher delay, and we have tried different order and different cutoff frequency. And we also had tried the Chebyshev type of filter. Hence, the optimal one that we choose is the IIR Butterworth bandstop filter, which second order, combined with the low pass filter, which third order, and the cutoff frequency is 0.35. For the part of frequency response plot of filter, here is the code. Here is the result of the plot. For the magnitude response, we can observe that the response has the flat pass band, which shows that it is a Butterworth filter. At around 800 Hz, the gain becomes zeros, and at around the 1400 Hz, the gain be reduced to 0.707 or negative 3 dB. For the phase response, we can observe the non-linear phase response, which shows that it is the IIR filter, and the phase shift is around 800 Hz and 1400 Hz.
This is the code for the Pro 0 plot. Then the function template is used to visualize the poles and zeros of a discrete time system in a complex template. The TL and Z are the vectors of zeros, while the EM and P are the vectors of poles. Then we can get the 3 plots. First is the plot of the bandstop filter. There are 4 zeros and 4 poles. The zeros and poles are 4 pairs of complex conjugates. Next, for the low-pass filter, there are 3 real zeros and 3 poles. In the poles, there is a real pole and a complex conjugate pair. The right-hand side of the plot is the Pro 0 plot for the combined filter. Where all the poles are within the unit circle, means that the system is stable. Here is the code for the filter impulse response in the time domain. The function STEM is used to plot the discrete sequence data. The BBS, BRB, and B are the filter coefficient of each filter. There are 3 plots of the filter impulse response in the time domain, which is the low-pass filter, bandstop filter, and the combined filter. The combined impulse response can also be obtained by convolving the individual impulse response.
This is the code for the frequency component after filtering. First is the filter audio magnitude plot. It uses frequency vector on the x-axis and filter audio FFT on the y-axis. Second is the filter audio phase plot. Same x-axis frequency vector, y-axis is the angle of filter audio FFT converted to degree. From the plot, we can observe the magnitude plot show peak at certain frequency, indicating the dominant component after filtering. The phase plot is almost flat, which might suggest a linear phase or constant phase shift. Now I show the audio. First is the audio after removing noise.
0125.
Second is the audio after removing the click sound.
0125.
After filtering, the results show the noise was filtered out successfully. The audio also sounds much clearer. This project shows that butterworth filters are effective for audio noise filtering and demonstrate how Dsp technique can be applied to enhance audio quality using MATLAB. That is all from our group. Thank you.